Now we're good.
Okay. Good morning, everybody. My name is Robert, and we are here to represent TensegrityWing. To my right is Sean, and Elias, and Kathy.
So project motivation. The shape of the airfoil on an airplane is very important to control, example, the attitude of an airplane. You have different control surfaces that control the yaw movement, the pitching movement, and the rolling movement. And in order to obtain the optimal shapes, typical traditional airfoils adjust, maybe say the flaps or the rudder in order to, as I mentioned, control the attitude. So right now, current airfoils use, for example, flaps and slats to increase the lift of an airplane. It's for example, say takeoff. And for cruise, you have the so-called clean airfoil shape. And for landing, you want to increase drag. So that's when, for example, the spoiler comes into play. But if we go on to the next slide, these traditional control surfaces create drag from energy inefficiencies due to discontinuities. And this leads to necessary thrust needed to propel the airplane forward.
So I'm sure some of you are probably wondering what tensegrity is exactly. It's a portmanteau of tensional integrity. So it's a structure where you have several 1D tensile elements and they stabilize a set of rigid bodies. So for a tensegrity wing, it would be comprised of a flexible skin and several 1D members, and via adding and releasing tension, we can morph the shape of the wing. So that's the goal of this project. We want to design a wing that can change its airfoil shape on demand using an internal tensegrity structure. So we want to model this wing and its morphing capabilities in ANSYS. And we would like to adjust the angle of attack by 5 degrees for cruising and 12 to 14 degrees for takeoff and landing. We hope to be able to achieve at least 3 different airfoil shapes. So the dimensions of the wing, the full wing is 250 millimeters, the chord length is 100 millimeters, and the maximum thickness is roughly 10. It depends on which airfoil shape you start with as your base. When we model this in ANSYS, we model only a segment of the wing, and that segment is 80 millimeters, give or take. Now, we need this wing to be able to retain its structural integrity in wind speeds of up to 75 meters per second, which is what we'll be using in the wind tunnel that we're using to test our wing.
Team roles. So we broke ourselves up into 3 main sub-teams: aerodynamics, structures, and fabrication electronics. I myself am the leader of fabrication electronics. Elias is the leader of aerodynamics. And Angie, who is not here today, is the leader of structures. Kathy, who is here, is one of the financial managers along with Angie. And
so the structures team is responsible for the initial airfoil selection. That just involves going to airfoiltools.com and downloading several different airfoil shapes. We then standardize the amount of plot types and upload it into ANSYS for 3D modeling. We're also in charge of choosing the configuration of the 1D members. That's just where they're attached to the airfoil and what shape they'll take. And after we do all that, we're in charge of simulating the deformation in ANSYS Mechanical. We use a thermal condition to adjust the lengths of the 1D members to deform the airfoil shape.
for the materials electronics team, we have worked out what the materials are going to be for the skin, the 1D members, which will be important for moving the wing. We've worked out what the fabrication of the wing shape is going to be like with material sheets. And our concern is the attachment of the 1D members to the airfoil skin. For electronics, we are working on the selection of the actuators, the microcontrollers, the motor drivers, any other circuits that are necessary in order to have it operate outside the wind tunnel when we test it in the wind tunnel.
So for the aerodynamics team, we want to obtain aerodynamic properties for selected airfoils by inputting geometric properties into profiling. Profili is a software that allows us to input these geometric properties such as the chord length, the thickness, or the mean camber. And we input a Reynolds number that we want to simulate an angle of attack. And we get the aerodynamic properties for the wing out. We also want to complete CFD simulations on ANSYS to validate what the software gives us. And given the time, if we have enough time, we want to apply thin airfoil theory to further validate our findings.
Alright, so for timelines, we have this quarter, next quarter, and the spring quarter of 2019, and this is a Gantt chart of mostly of actually technical stuff, like actually the selection, the aerodynamic, what the aerodynamics goes on, and stuff like that. So for fourth quarter, the air team will focus on pressure, find out the pressure distribution and the aerodynamic properties of the airfoil we're going to use and the wing. And the mechanical team is focusing on using CFD and FE to actually find out the mechanical properties. And the fabrication is to select some potential material and actuators according to aerodynamic and the mechanical team, and provide the necessary airfoil piece for the mechanical team for modeling. So for next winter quarter, fabrication will come up with a feasible fabrication plan and actually start fabrication, and structural team will hopefully finish the structural design, and the aerodynamic team is preparing for the wind tunnel testing leading the next quarter. And for the spring quarter, aerodynamic team will actually go do the wind tunnel test and use those data to compare between the wind tunnel data and the ANSYS data and hopefully hand calculation data. And the structural team will revise and optimize the design, and the fabrication team will finish fabrication and implement actuators and necessary electronic components. So we are currently a little behind schedule, but we'll hopefully we'll still be able to finish by the end of this school year.
So the progress we've made in materials electronics is we have selected shape memory alloys to be our actuators and to act as our 1D members, as they will be easy to work with for what we plan out for the wing to move and to operate in the wind tunnel. The aluminum 6061 is our material for the skin. We've chosen Arduino Uno as our microcontroller, and an 8-channel motor driver to provide our current electronic current for each shape memory alloy.
So far, the structures team has modeled 18 different airfoil shapes and their 1D members in ANSYS, analyzed potential structural integrity issues with regards to outside pressure distributions. We revised the 1D member layout. As you can see on the top, there's an X shape with 12 points of contact. We changed that to just 6 points of contact with 3 vertical 1D members. We found that we were getting better results in the deformation with just the vertical members. By altering the lengths by 5% of each 1D member, we're able to generate 8 different permutations for the changes in airfoil shapes.
So as mentioned earlier, the aerodynamics team has been able to obtain pressure distributions that have then been input into the ANSYS simulations. We're currently in the works of inputting the selecting airfoils into the software and see how the pressure distribution and aerodynamic properties change with each permutation.
Alright, so for fundraising, we have submitted a Euro proposal for this quarter, and hopefully next quarter, and for next quarter we'll write a proposal template and start going to contact potential companies for funds.
So the next thing the structures team will be working on is we'll be looking at different tensegrity structures and tensegrity wing designs that already exist. And we'll be trying to find different cell structures that we can incorporate into our wing that will allow it to achieve torsional deflection.
So for the aero, now we want to begin verifying our findings by completing CFD analysis on ANSYS. And we want to prepare for wind tunnel testing by reading up on how to calibrate the equipment, setting up meetings with the professors and the faculty that will give us access to the wind tunnel. And yeah,
fabrication, our objective is just to take the materials that we've decided on, the aluminum and the shape membrane alloys, and just test them and their properties, see if they would work out for our wing design. And we also plan to study on how to the necessary manufacturing processes to produce our material and make it work for our, shape it for our wing design. And we also hope to contact the manufacturing companies for information on the prices and the lead time.
So this is a budget we submitted based on the plan we have for now to manufacture the airfoil. So as we can see, we are using the actuator wires as thermal like control the wire that can change its length with it. And we're using aluminum sheet for skin so far, and we're using Arduino microcontroller and both are sheet hopefully to cut off for airfoil shapes. And those are just some basic tools. Since we're a new project, we don't really have anything to start with. So. We have 14 people on the project and 1 person being a volunteer. So we have about like 118 hours per week of like actual hours people are working on this project. And here are some references and questions.
Okay, thank you.